So we are going to continue our discussion with integer and fractional quantum Hall effect. And essentially what we are after is we would like to explain these features in the experimental data. So yesterday we discussed how to write ground state wave functions for n electrons for integer filling fractions and for fractional filling fractions. For fractional filling fractions, the Hamiltonian includes electron-electron repulsion coming from Coulomb interactions. And you can write down the wave function in what is called Laughlin type of wave functions, because it was first written for m equal to 3 or nu equal to filling factor equal to 1/3. And this is how it was written. It was a variational wave function. You write it like this, and you minimize the total energy of the system in the presence of interactions, and you find out what is the value of m. A general analysis revealed many fractions, many values of m, like 3, 5, 7, and so on, minimize the total energy of the system. Next, what we are going to discuss is what is called composite fermions. It is an interpretation for fractional quantum Hall effect that maps the fractional quantum Hall ground states to integer quantum Hall ground states. The idea is the following. So we can always write this in this way. The idea is that we notice that this part already includes all the Pauli correlations that should be there. So this part, it looks very similar to integer quantum Hall effect wave function. So if the idea is the following, to construct new quasi-particles such that this is the relevant wave function. So these new quasi-particles should have a factor that cancels this factor. So the new quasi-particles will behave as if the filling factor is 1. Let's try to see this in detail, and we will do this composite fermion model for m equal to 3, or the filling factor 1/3. And you can extend this analysis to higher filling factors also, to other filling factors. Now, what does nu equal to 1/3 means? That means rho electron over rho b. This is 1/3. That means so if you have what this means is that the number of electrons and number of flux quanta that are there in the magnetic field are not same. That means you have more flux quanta than the number of electrons. In particular, you will see that number of electrons is actually 1/3 of the number of flux quanta that are there. That's what this filling factor means. So you can think of this in the following way. I'm drawing by these arrows flux quanta. For every 3 flux quanta, you have an electron. And so on. What composite fermion model does is it says, let's look at this system in the following way. Let's draw one flux, let's leave one flux, and let's pair these 2 flux with the electron. And now we are going to consider the possibility that the electron-electron interactions, the various terms in the Hamiltonian act in a way that these two flux particles become intrinsic to electron. So they are not the electron, or we should no longer call this electron, and this is called as composite fermion. This particular object, for this particular object, the external magnetic field has reduced by a factor of 3. So one way to think of this is imagine that this particular object has two negative flux quanta attached with it. That will cancel these two flux quanta, and then the total magnetic field is going to be 1/3 of the magnetic field you started with. Another way to think about this is think of this as a bound state of electron and two flux quanta. And what this bound state will do is it will modify the property of these flux quantas in a way that it is not available as an external flux. Yes?
So I don't think I understand. Like the electron has electric charge, but the flux quanta have magnetic charge.
Yeah.
And are you saying in some sense they cancel out? Or?
No. So it is. Think of it as there is cancellation is intrinsic. So what I want to say is the following: if, for example, you put a magnetometer anywhere in the system to measure the total magnetic field, you will measure the total external magnetic field, which is 3 times the electronic density. You will measure any external device will measure the total magnetic flux. This cancellation is completely intrinsic. Only this new object sees, so it is, in some sense, this is an interpretation of fractional quantum Hall. So what it is saying is this composite fermion, because of these flux particles, it gives you this factor to the power 1 minus m that will cancel.
Are we saying that 2/3 of the measured extrinsic external field is due to the composite fermions?
Yes. So 2/3 of the magnetic field becomes intrinsic. And the reason it is not available is because of interaction. So this is not a, so let's say this is a way of interpreting this wave function. This is a way of physically understanding this wave function. Yes?
Sorry, what do you mean by intrinsic?
By intrinsic, I mean only this cancellation is only seen by the composite fermion. So if you, for an electron sees total magnetic field, but the composite fermion only sees 1/3 magnetic field, any external device will measure total electric field.
But these quasi-particles act as if they're in a magnetic field that's 3 times weaker.
Yeah. Now, if this happens, then what you have here is integer filling. You have same number of composite fermions and same number of flux particles. So in this, by using this construction of composite fermions, you can map fractional quantum Hall states to integer quantum Hall states. Now, these composite fermions, they are very tricky particles in the sense that they are not going to exist in vacuums. They will never exist in vacuums. They only exist in a certain many-body wave function. For example, this one. This is a wave function for n electrons, and the Hamiltonian, this wave function is ground state of an Hamiltonian that includes two particle interactions. Only in certain wave functions like this, you would observe these composite fermions. So you can't think of a composite fermion existing by itself. It needs many other electrons to and magnetic flux to have this kind of rearrangement. Yes.
So this wave function that you've written there is for the quasi-particle. You said that we can see the cancellation in like the power of Zj to Zk. Can you just go through that again, please?
So the claim is that this is wave function for the electrons. When you write the wave function in terms of composite fermions, this factor is no longer going to be there. So the wave function would look like the wave function for an integer quantum Hall effect.
Could you have these composed fermions but with arrows down instead of up?
So this is, I think last time when I did, I tried to present that. So the idea is that this cancellation of flux is intrinsic. So sometimes it is presented in the following way, that you have an electron, and now this electron, because of interactions and the presence of a gauge field, this electron becomes a quasi-particle which has two negative flux quanta attached with it that will cancel these two, and effective field is 1/3. So both ways of thinking about composite fermions is perfectly okay. The main point is, in the end, you will have one composite fermion and one flux particle. So it will correspond to integer filling. So again, this is a very simple mapping, and what it does is, now once we understand all these plateaus and features for integer filling fraction, we can map it to understanding fractional behavior of fractional quantum Hall states. And the mapping would say, whatever we did for electrons here, now the same thing happens, but it is for composite fermions. So next, what we are going to do in this last lecture is try to understand as many features as we can on this plot. And now we are going to focus on integer filling factor, because now we can understand all other plateaus at fractional values by thinking of composite fermions. Any questions? Yes.
Sorry, so when we include the flux quanta with the electrons and we get quasi-particles instead, why does that change the power of the leading factor of Z?
So now, now when you exchange two electrons, you're not exchanging two electrons, you're exchanging two composite fermions, right? So this is one wave function. I will write completely different. So also you can write next to it wave function for integer quantum Hall state. Now in integer quantum Hall, so these composite fermions, they do get a phase of, when you exchange them, they get a sign of -1 only. They don't get this prefactor. So that's how they are constructed. And if you want to do details, you can do a more detailed calculation also. And so there is an object in condensed matter that a kind of excitation that exists there in many fields, like vortices. And you can think of vortices as one flux quantum penetrating through these vortices. So you can imagine a situation where you have magnetic flux everywhere. Because of interactions, in terms of vortices, because of interactions, two vortices and one electron form a bound state. And now, when you're exchanging two electrons, it's not just two electrons, these flux particles will also have to get dragged with them, and that changes the ground state, the features of the ground state. So far, we have discussed how to write down the ground states. Another thing we can quickly see is, so it is very useful in the sense that if you encounter a new plateau or there is some new data and you want to make an attempt to explain it, you can use these kind of wave functions. They are very useful. In practice, you will have to do some numerical computation because these are essentially wave functions with very large electrons. So they are useful to explain the state itself or the state of matter corresponding to those plateaus. Next, what we want to understand is why we get these plateaus to begin with. So remember the classical result. So the classical result said, so this was known since 19th century, that the Hall resistance should go linearly with the magnetic field. This I can multiply by h over E, and I can write this in this way. And this simply becomes h by E square rho B or this simply becomes the filling factor here. Yeah. So if you are at filling factor 1/3, this will give you a value of 3 times h by E square, and that is what you have on the plot. If your filling factor is 1, it will give you h over E square. 2, it will give you half of h over E square, and so on. So all these values are consistent with what you see on this curve. But is this quantum Hall effect? No. What this classical result is some points on this curve. Actually, if you draw a fit to it, all these plateaus agree with the classical result at some points. So the classical result, in fact, suggests that there should be no plateau at all. So what we are really trying to explain now is why we get these plateaus. So to understand why we have plateaus, what we need is to include disorder in our analysis. Now, in the beginning, we said to observe quantum Hall effect, you need samples to be clean. But now I'm saying to explain plateaus, you need disorder. But the point is, you need disorder, but not too much. So what that really means is, in practice, no sample is free from disorder. So the constraint we are going to put is that there are impurities. So by disorder, we mean that the system has a bunch of impurities. These impurities can be positively or negatively charged. They are randomly distributed. You have some function, some electrostatic potential that is a function of x and y coming from these impurities. What we are going to assume is that the strength of this impurity potential is much smaller than h bar omega c, than the cyclotron frequency. So we have disorder in the system, but it's not large enough to wash out the quantum Hall effect. If you have a very dirty sample, what you will measure is the classical result. All these plateaus will wash out. So you go in the lab, you try to make sample as clean as possible, but you're never going to get rid of all the impurities. And after you go and try to make it cleaner and cleaner, and at some point you will get the plateaus. But at this point, still the sample has many impurities.
So if you have a perfect sample, would you still get plateaus?
So far nobody has been able to make perfect sample, but I think this theory suggests that so there is another interpretation which is based on topological considerations, and we'll talk about that next. But if you really are successful in without disorder, it is possible that there are no plateaus.
That's why we are putting this.
Yeah, yeah.
Okay.
Good luck making the
No, I'm not
clean
gonna
sample.
make it, just I wonder if you do the model, like consider you have a perfect thing, can you explain plateaus?
So, in fact, if one makes a perfectly clean sample and there are no plateaus, or you still get plateaus, then our understanding of this understanding will be put to question. So, it would be more interesting if somebody actually does that experiment. There'll be more open questions. So, for the moment, what we want to do is understand what this kind of potential will do to the eigenstates. So what we are going to do is we are going to do this analysis by putting a term in the Hamiltonian. And for this purpose, let's start again with the Hamiltonian. Let's talk about Hamiltonian without any impurity potential. Now, yesterday we solved this Hamiltonian in symmetric gauge, and we wrote down the wave functions and we talked about interactions. But now we are only focusing on the integer quantum Hall state, and it's extremely simple to solve this Hamiltonian in what is called Landau gauge. In fact, I will just write down the gauge and the wave function in 2 lines. So the choice of gauge now is that the vector potential is, there is no vector potential in x, in y it is b times x, and in z it is 0. So corresponding to this vector potential, we have magnetic field B along z. If I put this vector potential in the Hamiltonian, what I get is the following Hamiltonian. Now, this Hamiltonian in y coordinate, it only has terms that are py. So you can write eigenstates in as a product of eigenstate, a product. So you can use separation of variables. So psi xy you can write as psi x times psi y, and the wave function for y coordinate would simply be plane waves, because they are eigenstates of the momentum operator. So you can write down the eigenstates of this Hamiltonian. You can label them with k, where k is the momentum in y direction, e to the power iky, and some function fk of x. So now if you write down the Schrodinger equation, you will find that this is Any questions? Now, this Hamiltonian is just a Hamiltonian of simple harmonic oscillator, where the minima of the potential half m omega square x square is just shifted. It's not at 0. It's shifted by this h bar k. This is simply the simple harmonic oscillator Hamiltonian, and you can calculate the eigenstates of this Hamiltonian. The energy eigenvalues are given by h bar omega c n plus half, where omega c is the cyclotron frequency, which you defined as EB over m. And yesterday we also defined magnetic length. Let's just write it for reference, is h bar over EB square root. So you can again see that these energy eigenvalues do not depend on k. And this is similar to the infinite degeneracy in symmetric gauge that we talked yesterday. So all the energy eigenvalues or the spectrum should be independent of gauge. So there is an infinite degeneracy in this solution also. You can also write down the wave functions. The wave functions for these, they're the simple harmonic oscillator wave functions. So H with subscript n is Hermite polynomial. So what you can note here is that these are, you know these wave functions very well. They have a Gaussian factor and Hermite polynomial. So the wave function for x is a Gaussian times Hermite polynomial. For y, you simply have a plane wave. And this Gaussian, the location or the peak of this Gaussian depends on k. So just like in symmetric gauge, we saw that the wave functions do depend on the angular momentum quantum number. We chose the symmetric gauge, and there the angular momentum quantum number was important. Now we are in the Landau gauge, where the Hamiltonian has translation invariance in y. So the momentum in y is the relevant quantum number.
How are you able to write down the energy eigenstate, the eigenvalues?
So just by, so this is the simple harmonic oscillator. So I can write this Hamiltonian as momentum square plus half m omega square x square and figure out what this omega is. So I can map this Hamiltonian to a simple harmonic oscillator, one-dimensional simple harmonic oscillator Hamiltonian.
Okay, but there's also a constant term like the h bar squared k, or does that go into the momentum?
So a constant term that is independent of k, you can drop.
No, but that depends on k, the h bar squared k squared term.
So here you will not get any shift, but in general you can get a shift also. So here I'm just redefining x. So in the wave functions you will get this, but so I think, so you can just write down this Hamiltonian and solve h psi equal to e psi. Use the same tricks as you did for simple harmonic oscillator, and you will get this Hamiltonian. So
Potential's minimum is just not a x equals 0.
So you can just relabel, shift the origin. But it is an important thing for what we are going to do next. So this we know very well. Now what I'm going to do next is add something to this Hamiltonian that will make it a bit more complicated. What I'm going to do is I'm going to add a term corresponding to electric field. So what I'm going to consider is the following Hamiltonian. So I understand the confusion. If you have some constant in whole square, like this, sorry, let me write this as h bar k. If you have a constant whole square, then it does not appear. But if you have a term like this, then the shift will appear in the energy. So if you have this Hamiltonian, let's start with Py. What does this Hamiltonian mean? So this part is same as before. What we have done is, so we have two-dimensional electron gas in the presence of magnetic field. In Landau gauge, this is the Hamiltonian. But now what the additional term corresponds to a potential due to an external electric field. So we have assumed that we have applied some electric field along x-axis. And the charge of electron is minus E. So you get a contribution to the Hamiltonian that is given by this. Now again, assume in y coordinate still does not appear in this Hamiltonian. So you can solve this Hamiltonian again using the same trick. In y coordinate, it's plane wave. So here you will get h bar k. And now you can again complete the square and go through the calculation. But now when you calculate the energy values, you will get some additional terms that are left over from completing the square. And now these energy values will depend on k. So now what you will get is h bar omega c n plus half minus E times E there are many ways to write this. So now when you try to complete the square, there will be terms that you will have to add and subtract, and that means the energy will have these additional terms. So a quick takeaway, the infinite degeneracy that we were talking about is gone. Because now the energy eigenvalues do depend on k. So this is not surprising. Typically, when you add a perturbation, it can lift the degeneracies. And particularly, you have added electric field, and that does lift the degeneracy. And you can see from this expression, if you now write down the wave functions, of course, because now we have completed the square, the shift will be different from what we had earlier. And these wave functions now again, Hermite polynomials. So this shift that we get here is very crucial in energy. A, it lifts the degeneracy. Another thing that this tells you is, let's calculate velocity in y direction. So the velocity operator, if you have this spectrum, you can calculate velocity as 1 over h bar del over dky, which is just k, of the energies. So remember, this velocity operator is this first derivative of the energy, the spectrum. If you did this before, you would get 0. No velocity in y direction. Now, in the presence of electric field, you get a velocity in y direction. This is very crucial. Let's see the direction of this velocity. So we have electric field. Let's choose these coordinates, x, y, and z out of the board. So the electric field is in x direction. The magnetic field is out of the plane. This is our true deg. Magnetic field is in z direction. So the electric field is in x, magnetic field is in z, and what we have is a velocity in y direction. So we have a velocity, a drift velocity. So this calculation predicts that the particle will now drift in y direction. Let's calculate this velocity. If you calculate this, you will find out that this velocity is minus E over B. So this you've probably seen also in electrodynamics, that if you apply, in the presence of electric and magnetic field, the drift is not in the direction of electric field. it is in the direction of E cross B. So the velocity is in y direction, so that is minus E over B. And if you do E cross B is in minus y direction. Any questions? Yes.
So we put this in an asymmetric gauge so that when we apply the electric fields, we kind of already have broken symmetry in preparation. What would happen if we added that term to to what we had written yesterday in terms of the symmetry?
Symmetry gauge. So the conclusion would still be same, that it drifts in E cross B, but then the calculation will have to be done. So what I'm concluding is not just Vy is this, but what I really want to say is the conclusion is that the particle is now drifting in a direction E cross B. So this direction need not be in Y. In this particular gauge choice, as you said, this direction happens to be Y.
Is there a way to see the relationship between the states in this gauge and the states that we found?
Yes, I mean, you will have to do this transformation, but it's slightly messy if you think of these wave functions. For example, these wave functions, what they represent are Gaussians that are peak, so at some values of x naught. So we are completing the square in x. So these are really Gaussians at various values of x that depend on k. So the y momentum gives you the location where you have the Gaussian peak. And then there are Hermite polynomials also in x. Within this Gaussian envelope, there will be Hermite polynomials and then plane waves in y. So on top of this wave function, you will have to multiply by this e to the power minus a phase factor corresponding to the gauge transformation, and then you can go to the symmetric gauge. What you will find in symmetric gauge is this will turn into, let's try it here. So this will turn into, okay, this is into concentric. So again, it will be Gaussian. But now, so you remember from this in complex plane, we also had a Gaussian, e to the power minus z bar. And this Gaussian was located at the value corresponding to m, same as here it corresponds to k. So there are a lot of similarities, but to go from here to here, you will have to do this, multiply by this phase. That depends on x and y, depends on r. Yes.
This electric field, in terms of the Hall effect, does that correspond to the current that's flowing?
No, not yet. So this is just a toy model. And let me write down the conclusion. Later on, I'm going to replace this electric field by the field generated by the impurity potential. So this has, at the moment, nothing to do with the Hall field, with the applied current. So the drift is in direction E cross B. Now let's calculate the current. So the electronic current density this will be given by the charge of the electrons times the electron density n naught times the velocity in y, which is a function of k. Now, this velocity, because of the minus sign, this will be in, so the electrons are going to drift along minus E cross B. So what we are saying, what this analysis suggests is that if you have zero electric field, and magnetic field B in z direction, what you have is electrons moving in circles. If you add to this an electric field in x direction, then they will drift, the electrons will start drifting in minus E cross B. So what you will have is a picture like this. So they're drifting in positive y direction. Any questions? So now I'm going to generalize this result by replacing this electric field here in the Hamiltonian by this electric field by minus the gradient of some potential V of xy. So there I assumed electric field in x direction, but now what I'm going to do is this electric field is the local electric field coming from this some electrostatic potential. So the direction of electric field will depend on this potential now. Now in this analysis, the direction of electric field, so electric field itself was uniform, and as a result, the direction of drift for electrons, which is minus E cross B, was uniform, is along y direction. But if your electric field is not uniform, is changing, is locally changing, that means the direction of drift for electrons will be also changing. Yes? So what is the direction of drift? So electrons will drift along minus E cross B. So this you can write as minus Z hat cross gradient V also. There are many ways to write this cross product. But the key point here is that the direction is now locally changing. It will depend on the local direction of the electric field. Now let's figure out what this direction will be. Now, the direction of drift, so for a general potential Vxy, can we guess where the drift will be? Now, the direction has to be in xy plane because magnetic field is uniform and it is in the z coordinate. And so it should be in xy plane. And electric field is in xy plane because this potential is a function of xy. So it should be in xy plane, but it should be perpendicular to electric field. We know contours that are perpendicular to electric field are basically the equipotential contours or the equipotential lines. So equipotential lines corresponding to this potential will be the direction of drift. So what that means is consider in this two-dimensional space that some equipotential contour that looks like this. So you have some electric field, some magnetic field. So you have magnetic field B in z direction. You have some locally some electric field. Say the electric field here, the direction of electric field is here locally, and along this, say the direction was here. So what will happen? So what I've drawn here is an equipotential line. What will happen is the electron will drift now. Here, the drift is going to be, the drift velocity is E cross P, negative of this. So the drift is along here. This is how the cyclotron motion will look like. So you have circles, but with a drift in this direction. And here, the drift will be in opposite direction. Any questions? So next, what I'm going to do is I'm to I'm going to imagine this potential as one coming from the impurity potentials. So I'm going to draw a figure and I'll try to make it big, and we are going to use this figure to understand some of the features on those curves. So imagine that you have some negative impurity here and some positive impurity here. Now, very close to this impurity, so how does an electric potential go? So electric potential goes as 1 over R. Far away from this charge impurity, the value of potential will be weak. Very close to it, it will be strong. And if you draw equipotential lines very close to it, they will look like this. Right? Now, the direction of electric field locally for this case is towards the charge center. So what is the direction of magnetic field is in z direction. So the direction of drift is going to be again E cross B. So E is in this direction towards the charge center. So E cross B in this direction, negative of that. So the electrons are going to drift in this direction. For all these equipotential lines that are closed contours, very close to the charge impurity, the electrons are going to drift like this. So they will drift in a circle. That means they will get localized. They can no longer travel from one end of the sample to the other end of the sample, and they cannot carry current. Same for these positive impurities. Again, the direction of drift. Now the field lines are out from the point charge. So you have E cross B, and so they're opposite to this. So here the drift is in counterclockwise direction, but again, the electron is going to get trapped or localized. Any questions? So what happens is, typically you try to make a clean sample, but it still has many impurities. And what these impurities will do is they will localize electrons. So what impurity potential or disorder does is it localizes electrons. Now, it is also possible to have equipotential lines that look something like this. So you can already see far away from the charge, the value of the potential is smaller, is much small, but you could have an equipotential line that is like this. Along this equipotential line, so it is the electron will drift along here in this. Along this contour, the electron is going to drift like this. You could also have similarly a equipotential line, equipotential contour that is like this, where the electron will now drift like this. So the point is the following: because this impurity potential is really random, you have no way of knowing, many such trajectories are possible. Some localized, some can be extended. So what we are going to do next is try to see how this affects the spectrum. Any questions so far? Yes.
You said we should have disorder, but not too much disorder. What would the case with too many impurities look like?
So if you have too many impurities, all of the electrons will get localized and system will become an insulator. But there is still a possibility that this insulator, so we are going to talk also about a concept that is, so basically we'll talk about edge states. So you could have an insulator that is insulating in the bulk because of too many impurities, all of electrons in the bulk are localized, but this insulator can still transport current because it's what is called a topological insulator and it has certain edge states. So we are going to discuss that also because in quantum Hall effect, so this is sort of a precursor to topological insulators. So we already see such features and we are going to discuss that. But in the bulk, if you have too many impurities, all the electrons in the bulk will be localized and no current can flow through the bulk. But there is a possibility that the current can still go around the edges. Any other questions? So we have seen the notion of two types of states so far. One we will call these localized states, and one we will call these extended states, which are still states in the bulk. And we call them extended because they can really move from one end to the other end. So now let me draw this figure. So what I'm trying to plot is density of states and energy. So the various energy levels in this problem, let's start with V impurity as 0. So that means there is no electric field in the Hamiltonian, so the energy levels are infinitely degenerate, and they are located at n plus half h bar omega c. So this is half h bar omega c, 3 half h bar omega c, 5 half h bar omega c, and so on. And the density of states, it's really infinitely degenerate. So I'm going to draw it with these arrows. What that means is that these states are infinitely degenerate. This is how this plot looks like. So you really have infinite states, but at discrete values. For each of these discrete values, you have very infinite number of states, but the sample is going to be finite. So this degeneracy is going to be finite. It's still going to be very large, but it will be finite. And yesterday we saw how we can estimate this degeneracy for a finite system. Now, what I'm going to draw next here is what happens to this in the presence of impurity potential. Now, imagine the states that were here and think of what happens to these states in the presence of impurity potential. So these states are highly degenerate and the wave functions are different by different values of k. So this has infinitely degenerate, and each state in this infinite degeneracy can be labeled by a value of k. Depending on that value of k and whether the potential is attractive or repulsive, you will get an energy shift. That is this term here. Depending on the label k and whether the potential is attractive or repulsive, that is this E here, you will get a shift in the energy. So this shift can be positive or can be negative. So a lot of these states, some can go below, some will go above. And all of these states that go above or below, so if the shift is very large, that means you're really at these circular equipotential lines. That means you're very close to a charge center. And all of these, for large shifts, all of these electrons are going to get localized. There can still be some extended states that are drawn like this, but you can already imagine from this figure, the value of potential for this line is very small. This line is very far from all the charge centers. So the shift corresponding to this trajectory is going to be small. So these electrons are going to stay in energy more or less close to where they were before. So what this plot will look like now is the following. So half h bar omega c So this is what is also called as broadened Landau levels. So these are Landau levels, infinitely degenerate. You add impurity potential, and what you get is broadened Landau levels. So these, let me shade some of these. So these are all localized states. So these are all localized states. And in the center, for the energy values that are very close to the energy values without any impurity potentials, you still get extended states. Any questions about this figure? So next, what we are going to do is try to understand those plateaus. Now, imagine that you're sitting at one of those plateaus corresponding to one magnetic field. And what we are going to do is decrease magnetic field. If you decrease, yes?
Sorry, with this picture here, you said that the electrons are flowing along lines of equipotential. On lines of equipotential, I thought they weren't allowed to cross.
Oh, well.
The localized ones that have to follow.
Yeah, I mean, this can be, like, it really depends on the random potential. You can imagine something like this. I'm just trying to draw a bunch of equipotential lines. Yes?
So why the energy of the extended states are not shifted?
Sorry, extended state.
So the energy of the extended states are not shifted.
So I'm just trying to, you have to, in principle, do full calculation to see what the shift is. What I'm saying is the shift is very small, motivated by following reasoning. So the electric potential goes as 1 over R. And this is potential coming from these point charges, which are really impurities in the system. So if you are far from this charge, the potential itself is very small. And typically, you would expect these extended trajectories to be far from the point centers. Otherwise, the equipotential lines are going to be circles. So the shift is still going to be there, but it's going to be smaller as compared to equipotential lines that are very close to charge centers. Yes?
And do we think of the difference between extended and localized states? Is it like a gradual spectrum, or do we categorize them exactly?
So the difference is, in this sense, whether you can transport current, whether these states, so this is the spectrum, but there is also wave functions corresponding to them will be very different, and that's why we are calling them extended and localized. So the wave functions corresponding to localized ones cannot carry any current. So now imagine that you decrease magnetic field. What will you do? So there are a bunch of equipotential lines. I can draw many. Like there will be a whole lot of them. It all depends on the impurity potential. And these equipotential lines will be different for different samples also. Okay, so if we decrease B, what will happen? A, we know that the degeneracy of Landau levels will decrease. Right? So yesterday we calculated the degeneracy for the Landau levels, and we found out that the degeneracy is given by EB over 2 pi h bar. So this is the maximum states that can be there. And we did this estimate by assuming a finite disk. So you can see if you decrease magnetic field, you decrease these degeneracies of these states here. Also, what decreases is cyclotron frequency. So we can see the omega c is EB over m. So these levels are also close to each other. So there are two effects. If you decrease B, you decrease the degeneracy, and you also decrease the energy separation. Now imagine that you have fixed number of electrons. Say you have 1,000 electrons, and the degeneracy of this state is also close to, each of these states is also close to 1,000. That means, so for this one particular case, for one particular value of magnetic field, these 1,000 electrons will occupy, say, this level only. And this level is fully filled. Now you decrease the magnetic field, the degeneracy of this level has reduced, and also energy separation has reduced. So these 1,000 electrons will now have to occupy states in the higher Landau level. Is that clear? So if I decrease magnetic field, I will have to start occupying states in the higher Landau levels. Now, when this happens, that you have to start occupying states in the higher Landau levels, the states you will occupy first are going to be these localized states. You occupy the next available energy state, and these localized states, they don't carry any current. That's why you can decrease magnetic field, but the current does not change. And that's why you get the plateaus.
Explain that again, please.
So if I decrease magnetic field, I should occupy states in the higher Landau level. The first state that I'm going to occupy will be the lowest in energy. So imagine that you're here and you're decreasing magnetic field. The degeneracy of this state has become smaller, so you have to occupy higher states. But the states you will occupy will be these ones, which are localized. Eventually, you will occupy extended states, and then the current may change. But there will be a whole value of magnetic field that you can decrease, but still the current, the transport properties will not change because these states simply cannot carry any current.
What provides, so when you decrease the magnetic field and the energy of the electrons has to increase, What,
Yeah, effective chemical potential is increasing. Yeah.
what provides the energy?
So we are just imagining T equal to 0. We are imagining Fermi energy in the sense that we have a bunch of levels and we start with fixed number of electrons and we are trying to calculate the new ground state. So the distribution of states is different, and I will start, in each case, I will start filling up the system one by one, and the ground states for different values of magnetic fields is going to be different. So now we have explained one feature in that plot, and that is the plateaus. So we don't have too much time, so I'm trying to go over a few important things. So we still have two questions to address. A, what is the role of these extended states? And B, why? So we know now how we can get plateaus. We need disorder, not too much, but we still need disorder. But we still have not explained why we get plateaus at precisely those values, at precisely the values corresponding to h over e square. So these two questions we need to explain also. So what we are going to do first is, let's quickly talk, we can talk about these extended states. So as you can see from this contour, you can have these curves, these extended states. So if you are applying now a Hall current, say the current is in x direction, you can imagine that electrons are going this way. If you imagine that the electron is on this equipotential trajectory, it will come back. Or at some point, it can also jump to this trajectory and come back. That means that these extended states provide many possibilities for scattering. That means an electron that enters from this end may not make it to this end because it may get scattered. So there might be some overlap in the wave function for electrons here. So these extended states you can get an electron scattered into another extended state. But if you think about wave function overlap for a state here and here, that's going to be almost zero. So a localized state, you're not going to get scattered into an extended state. So the role of these extended states is to provide a scattering mechanism for this longitudinal current. And when you measure the longitudinal resistance, and this corresponds to the graph below, that is Rxx, you see bunch of features, oscillations, and like sometimes it drops to zero and not. So the role of these extended states is to explain Rxx, why potential drops in the longitudinal direction along x. So we have current flowing in x, and you can measure some potential drop in y. So you have some resistance in longitudinal direction that comes from these extended states. Next, what we are going to talk about is why we have Hall conductance. Yes?
I don't understand that about the drop in the resistance. It's like,
So the point here is that the extended states, they provide possibility for a particle, an electron that is injected from this end to go through the bulk and get scattered into something else. Actually, that I understand the confusion. The reason it is not very clear is because we are still missing one more piece, and that is the edge states. So let's just discuss that. And I will complete this picture, and then the role of these extended states will become more clear. But for the moment, we are making a statement that the role of these extended states is to explain Rxx. So next, what we are going to talk about is another set of extended states, which are called edge states. Now, one crucial piece that we have missed in this analysis is what is called confinement potential. So you can ask yourself question, what defines the boundary of this two-dimensional electron gas? So you can imagine a confinement potential. So V confinement, let's say we are talking about V confinement in Y direction. And what does this mean? This means this is a potential that is going to confine all the electrons in finite region. So this is what you do typically in the experiments, and it will look something like this. So this is, say, top edge of the sample. This is bottom edge of the sample. And you can think of this potential as particle in a box. The value of potential is very large at top and bottom edges. That means the wave function must vanish. And effectively, you have confined all of the electrons between top edge and bottom edge. Now, this potential does not depend on X by definition. So you want to confine everything in Y. This potential does not depend on X. If I were to draw equipotential lines corresponding to this potential, I will have a lot of equipotential lines that will be running parallel to the x-axis because this potential does not depend on X at top edge for each of these values and at bottom edge. So let me draw those. So in this curve, I will have to draw equipotential curves on equipotential lines on top edge and on bottom edge. And there could be many lines like this. We can also figure out what the direction of electronic drift will be. Let's do that. So on top edge, the potential is, what is the derivative? The slope is negative. So the electric field is negative of that. So the slope is negative. That means the electric field is in positive Y direction. So the electric field is in that direction. So E cross P is in this direction. The electronic drift is minus E cross P. So on top edge, you will have electrons drifting like this. Similarly, on bottom edge, you will have electrons that will drift along positive X direction. Any questions? Now, so far, I've considered confinement potential in X, but this two-dimensional electron gas is also, in Y, this 2-deg is also confined in X. So you will have similar potential in X, and you will have equipotential lines also on left and right edges. So what you will have is what is called edge states, and they will be running all around the sample. Any questions? These edge states are running all around the sample, and you can also check that these edge states are chiral. Now, what does that mean? That means they go in only one direction. So in this case, this particular edge state, the electrons are going counterclockwise. What that means is no matter what, there is no state, it cannot be backscattered. What that means is an electron in a chiral state cannot change its direction, cannot go backwards. It will continue to move in that direction. So on top edge, for example, this electron can only move in left direction. So sometimes they're also called as left movers, these chiral electrons. You only have left movers on top edge. What that really means is that the states are chiral. That means you cannot scatter these electrons. You cannot make these electrons move in the right direction. They will only move in the left direction on top edge. That means if you inject some current in top edge, it will flow without any problem, or it will for sure make it to this end, because there is simply no other way for these edge states to get scattered, to reverse their direction. However, if you apply, say, some current in this edge state here on this left edge, before it makes it, so now this is in our experiment when we do apply current, we are applying current in X direction. So this is the I. So first let me summarize about edge states. We can draw a bunch of these equipotential lines and their trajectories. One place we are almost guaranteed to find extended state is on the edges because of the confinement potential. So you're almost always guaranteed that you will have these edge states at the edge. Because of the presence of magnetic field, what you have is chiral motion of electrons. So electrons in this edge states move only in one direction. So we have edge states coming from the confinement potential. Now let me go back to explaining RXX. Now you can imagine that you injected some electron here. So the current is in this direction. That means electrons are moving in the opposite direction. So the electrons, they can go to the other end along the edge seamlessly, right? But it is possible because of these many extended states that they get, there is a process where there is a finite wave function overlap with one of these extended states. For example, it may go like this. Before it makes it to there, it sort of comes back. So in this way, these extended states provide scattering mechanism that can give rise to resistance, finite resistance along the longitudinal direction. So this current will not make it there. As a result, you have finite resistance. So it really depends on what the equipotential lines look like. So this is what I meant by saying that these extended states, they explain RXX, or they give rise to the behavior of RXX. So the features in RXX can be very complicated, and it depends on the contour lines. Yes?
So just to be clear, at the extended states is when, so in between the two extended states is when you have zero resistance, and that's because?
So it's also possible that sometimes, for example, you could have an electron like going from here to here, or sometimes you could have extended states that simply go through the whole sample. So if that is the case, you will get RXS 0. So that does happen. What that means is, so it really depends on the sample. You can also see that RXX is, I think it's better to look at the figure that you were handed out. You can see that RXX is not always 0 for all of the plateaus.
When it is zero.
When it is zero, you can think of this as an extended state that connects from one end to through the bulk. It connects from one end to another end, and this state. So there is no scattering process. So the electron. So there is a possibility of there is one possibility or one process where these extended states will transport electrons through bulk without any scattering mechanism. If you have equipotential contours that do percolate, that connect one end to the other end. And it is possible because if you start with very large degeneracy, you can draw equipotential contours, and typically when you draw equipotential contours, this is very rare. It's very rare to find equipotential contours that really connect the two sample edges. But when you find them, then the resistance will drop to zero. So I think that would explain. So they are very rare, and that's why you don't see them at all of the plateaus. And yeah. So to do this analysis more concrete, you really have to figure out what the potential is, what the landscape is. But this is just a general understanding of this phenomena. So next is how to figure out how many edge states, will be there. Now, this is where we have to do some topological analysis. So this course is about to end, so I'm only going to mention a few words about edge states and mention how that comes into the picture. So it's once we have the eigenstates of the Hamiltonian, it's very straightforward to compute a number. And this number is called Chern number. So it's straightforward to do this combination, this calculation. So I'm defining this number, Chern number, as following. This A is not the vector potential. This is something that is called Berry curvature. What A mu of K is, this Berry curvature, it is simply the eigenstates n, the gradient in mu direction, what these n of k are, these are simply the eigenstates. So in general, the energy eigenvalues may or may not depend on k. So I'm just writing it like this. So if you know the eigenstates, in principle, you can calculate this A, which is Berry connection. And then using this Berry connection, you can integrate over this in the following way to calculate Chern number. You can show this Chern number is going to be an integer. Now, how does this enter the discussion of quantum Hall effect? So let's say this is 2-deg. In general, you can have, so this is vacuum, this is our 2-deg. Outside this, we have vacuum. Vacuum has Chern number 0. So in vacuum, you have no particles. All these eigenstates are just 0. Chern number is simply 0. When we calculate Chern number for different ground states, depending on the ground states for different values of B, you can go through this analysis. So now you know how to write down these eigenstates and so on. You can go through this calculation and you can calculate Chern number corresponding to these plateaus. You will find Chern numbers corresponding to integer quantum Hall effects. These Chern numbers will be 1, 2, 3, and so on. Imagine if this Chern number for the ground state corresponding to these plateaus is n. Now, think about what happens at this edge. At this edge, you have to smoothly go from a Chern number that is n to a Chern number that is 0. That means this cannot happen. These are two topologically distinct phases. This simply cannot happen in reality. The only way it can happen is if this Chern insulator or the ground state corresponding to this Chern number closes down, the gap closes down, and it opens again. What that means is there is a theorem, the index theorem, that guarantees that there will be certain edge states at the boundary between two different Chern numbers. And the number of edge states is given by the difference between the Chern numbers on both sides. In this case, on one side, we just have vacuum. So the difference of Chern numbers is n. That means on this edge, there are going to be n edge states. Now, each of the edge states, as we discussed, once you are in the edge state, they are chiral. There is no way you can scatter. Each of these edge states contribute the full value of conductance, the maximum value of conductance. The maximum value of conductance for one channel is E square over H. So if you have n edge states, that means you will have a conductance of n E square over H. And this is now we are talking about Hall conductance. That means Hall resistance of H over n E square. So this is how topology comes into play, into explaining why precisely those plateaus. So that really depends on how many edge states are there. So we can calculate that, and for each edge state, there is a conductance of E square of H. So if there are in general n edge states, you get these plateaus. So the precise quantization, the precise values of integers comes from this topological analysis. From the fact that the ground state correspond, the wave functions that we wrote down, the ground state wave functions corresponding to this integer filling have this number. When we compute this number for these ground states, it's not 0. So these states have topological properties, will have edge states. So I agree this is not a very good discussion, very detailed discussion, and I think you will learn more about this in some other courses. And this is also related to topological insulators, which are new materials that are discovered almost a decade, 7-8 years ago. And there are a lot of, so what we did in this course is we learned a lot of tools. We learned how to model a condensed matter system which can have many electrons. And hopefully you will use these tools. You can use these tools in research. There are new materials that are being developed in the labs, and they throw surprises. You do experiments, and sometimes you find that the material is not behaving the way you would expect conventional material to be. And you can use these tools to try to predict why the system is behaving in a certain way. Again, I would say, to close this course, I would say one last thing, which is, remember the first thing we discussed? The fundamental particles that involved in this course are just electrons. They are very well understood. We know its charge and mass. But yet, when you put a very large number of electrons together, they can behave in very surprising ways. So that is what makes condensed matter interesting. Not the fundamental particles that are involved in the systems, but the fact that you have a lot of them and there are many interactions that is going on between them, and this will give rise to surprising properties, surprising new phases, and many exciting properties that come with these phases. Okay, so thank you very much.